I think I took a look. Give me a second. When did we start? It isn't it? Okay, I'll pick it up. Thanks. Yeah. I think so. I think I'm good. I think we should be starting. I haven't tried using the phone, but yes.
Right. Have a good session.
All right. All right, let's get started. Okay, wonderful. Welcome back from lunch. Please don't fall asleep. Standard rules apply. If you fall asleep, you have to buy me something later. Not if I don't catch you, but pay attention to the front of the room. All cell phones should be off. What else? I guess the standard Notewell stuff. I'm not going to actually show you the Notewell. I'm assuming you've read it somewhere. If you haven't read it, walk into one of the other sessions. You'll find it there. What I will ask is for a Jabber, somebody to look into Jabber and come up and ask questions. A Jabber scribe. I need a Jabber scribe. We can't move on without one. You'll do it? Excellent. Lawrence Stewart gets a cookie. I was actually going to get you all those things that kids are playing with these days. Fidget spinners. Sean Turner's idea. Oh, no, sorry. Rich Salz's idea. I also need a somebody to take down minutes. I'm going to start calling out your names. You will be embarrassed. Marcelo, you're shaking your head. You know, I take that as a yes. Are you going to take down minutes, Marcelo? Oh, excellent. Thank you. Wonderful. This works. And with that, I'm going to try and plug myself in to show you the agenda. The agenda is slightly different. I'm going to post a new agenda online. It's slightly different from what we have. Actually, you know what? I'm not going to show you the agenda. You can look it up online. I want to move quickly to the talks. The agenda is slightly moved. I'm going to have Toke come up and do his presentation first, but the rest of it is roughly the same. I'm also inserting Roland Bless for about 5 minutes right after the BBR talk. Those are the only two changes. Otherwise, the agenda is the same as what you've seen. And with that, I'm going to have Toki come up and start the first presentation. Oh, good. Well, there's the agenda. You can take a look if you want.
Do you also have my slides?
I have your slides coming up, sir. Oh, annoyingly, that happens. Oh, one thing before I start, I am actually going to enforce time limits. We can't get to the end of this meeting if we don't do time limits. You're already 5 minutes behind time. I know that, but we're going to try and I'm really going to enforce time limits. So take it away, sir.
Right. So, hello everyone. Am I in the pink box? Enough. So, my name is Toke Holm Jørgensen. I'm going to speak a little bit about some of the work we did on fixing buffer bloat and applying AQM techniques to the Linux Wi-Fi stack. So this was a paper that was presented last week at the Usenix Annual Technical Conference. Next slide, please. And since there are strict time limits, I'm going to talk mostly about the buffer bloat side of the issue. We also looked into this issue of airtime fairness in Wi-Fi, and you'll see a bit of that, but I won't go into that in detail. But first, I always like to start these sessions by asking the room, how many of you use Wi-Fi? And how many of you are not listening? As you may have noticed, especially not so much here at the IETF, but if you have a home router at home, sometimes the Wi-Fi is kind of flaky. And one of the issues that causes this that we've looked into here is buffer bloat at the Wi-Fi link. Next slide, please. So I assume most of you know what buffer bloat is in here. But the thing we saw here was that we have these techniques, AQM algorithms, queuing algorithms, and so on, that we can apply to wired links that work really well for pretty much eliminating buffer bloat in most cases. But for the Wi-Fi stack, we still saw hundreds of milliseconds of extra buffering in the stack, even when applying state-of-the-art AQM to the interface. Next slide, please. And so we set out to try to fix this, and this has gone into Linux versions 4.9 through 4.11. And as you can see, we saw this nice order of magnitude reduction in latency under load with this solution. Next slide. So some of the constraints and some of the reasons why previous solutions to buffer bloat do not work well for Wi-Fi is that there are these constraints in how Wi-Fi works. And Wi-Fi has this concept of traffic IDs where packets going to different stations have to be queued together so that we can aggregate them at the TID level. And we also need to handle reinjection of packets for transmission. And this means that we cannot have just one managed queue at the interface level, because we cannot just tell a queue, please give me 10 packets going to this destination. So we need some kind of queuing structure that allows us to split up packets going to different destinations. And then, of course, we need to keep the hardware busy, and we need to run this on really small embedded boxes. And we also do not want to modify the clients to achieve any of this stuff. But especially the first 2 points mean that we cannot use the existing buffer bloat solutions for Wi-Fi because they're simply not capable of doing this. Next slide. So what we did instead was, for the queuing part, we designed a new queuing structure, which is not at the interface level, but which is sort of integrated with the MAC layer in the Linux kernel. And it's based on FQCoddle. But in the straightforward way of applying FQCoddle would mean we would have 1,000 queues for each station associated to a wireless access point, and that's prohibitive for very small devices. So instead, what we did was we designed a structure. I'll show it to you in a bit, which has this global pool of queues that we then dynamically assign when we hash flows into them. We then assign a queue to a station, and that means we can reuse the same pool of queues no matter how many stations we have. And that means that we can then support this per TID dequeuing and scheduling that we need to aggregate packets for Wi-Fi. And then the grayed out thing here is the airtime scheduler. In the same work, we also designed a scheduler that uses some of the same techniques from FQCoddle, a DRR-based scheduler, to sort of make sure all stations get the same transmission time. And I'm not going to go into the details of how that works, but you'll see it in some of the result graphs. Next slide, please. So this is the Linux kernel queuing structure. On the left here is before, and here is after we modified it. So the things to notice here is this queuish layer. This is where you could install your AQMs beforehand. But what we have down here at the driver level is another bunch of queues, and these can be, this is sort of the source of the 100 milliseconds of queuing latency that we saw before. So what we did was we got rid of the queue disk layer completely by bypassing it at the Linux API level, and then in the Mac layer, which is the sort of the library that implements the Mac protocol for 802.11, we then assign the packet to their TID and then put them into these different queues where we have the global pool of queues I was talking about, and then we assign them to each TID, and then we apply fqctl between the queues currently assigned to this TID. And then there's an overflow queue in case of hash collisions, but that's sort of a minor detail. And then the only thing left in the F9K driver is now the retry queue, which is where packets that fail to be transmitted get re-injected, and that's basically just a priority queue where when you then transmit next time, you will retry the packets before dequeuing other packets. So this means we now have the managed queue here is way closer to the hardware. This is only 2 aggregates, which depending on your rate is on the order of 10 or 20 milliseconds in most cases. Next slide. Then we did some evaluations of this thing where we sent data from a server to 2 fast clients and a slow client. This was also to look at the airtime fairness issues. And we've used the normal FIFO queue, which you should all know by now this sucks. And then we have fqctl as sort of the best we can achieve with AQM latency. And then we have fqmac as the restructured queues. And then we have the airtime fairness queue as the last one. And so looking at the latency first here, we see that we go from, of course, FIFO, this is a log scale, obviously, so we go up to almost a second of latency with a FIFO queue. With fqctl, we reduce it somewhat. For the fast stations, we go down to about the 50 millisecond mark. And then for the fqmac, our new queuing structure, we go all the way down to 10 or 20 milliseconds. Next slide, please. Throughput also improves actually when we apply these modifications. And I'll go into the reason for this before. Of course, just applying fqctl actually improves throughput. But for the fast stations at the cost of the slow stations. So the average is the sort of aggregate throughput for the whole network. And the reason for this is on the next slide, which is the airtime usage for each station. So the percentage of time that each station spends transmitting. And the reason this improves from FIFO to fqctl to fqmac is that we actually increase the queuing space. So beforehand, you had a very reasonably small queue at the very lower layers, which would tend to get flooded with packets waiting to go to the slow station. And that meant that the slow station would take up almost all of the airtime in these 2 cases. It gets a little better here because you have better queuing, or you have round-robin queuing at the upper layer. But just applying this queuing structure at the MAC layer means that we can now have enough queue space to always have packets for all the stations available. So this is due to improved aggregation for the fast stations. And then, as you can see, when we apply the airtime scheduler as well, we get pretty much perfect airtime fairness, even though the stations differ in throughput or in rate by an order of magnitude. Next slide. We also evaluated the impact on different applications of these changes. We looked at HTTP load time, and we looked at VOIP performance by calculating synthetic mass values for the different cases. So the HTTP load times, as you can see, this is also a log scale. So this is, I think, 35 seconds to load a rather large web page, which we bring down to a few seconds in the best case. So this sort of reflects both the throughput and the latency. So the small page here is dominated by the latency. We can get down to almost 0 in the best case. And the large page also gains more from the changes in throughput, obviously. And next slide. So the VoIP test here, I'm not going to go into whether or not like this actually corresponds to actual voice quality, but if we put that aside for a moment and assume that it does, what you will see here is that 5.0 is at 1.0 is completely unusable for best effort traffic. So the best effort and voice traffic is the 802.11 queues. So in 802.11, you have a voice queue where you can get priority at the MAC layer. And so the thing to notice here is that with these changes, we now achieve better performance for best effort traffic than we did before with diff served traffic that gets priority at the MAC layer. So this means that we can now run our voice applications as best effort traffic, which is nice if we do not control the markings of the packets or if they are removed somewhere in transit. So this is pretty promising, and we have some plans to look into applications for this. But just to show that for real application traffic, we actually get quite a bit of an improvement as well. So as a summary, we've in this work, we've reduced Wi-Fi buffer bloat by an order of magnitude, again. And we get almost perfect airtime fairness with the scheduler as well. And this, it's a lightweight deployable solution. It's already in mainline Linux. If you run an open source firmware on your home router like OpenWord or Lead, you can get this now and run it, and it really improves things. And code, data, etc., available there. But otherwise, questions? No? How am I doing on time? I have some more graphs I can show if you want.
Thank you. You're doing really well on time. Oh, Randall's. Randall, you're up.
Hi, it's Randall Jessup, Mozilla. So it looks like this would have a significantly positive impact on Wi-Fi with WebRTC, in particular because typically those aren't diff served, and so not only should the audio avoid a lot of buffering, but also video recovery time from packet losses or other things when you have a round trip to do a NAC or whatever should also be dramatically improved. Have you done any testing with WebRTC? One other question I had was, so there is one downside to this, though maybe not large, which is the slow stations. Have you done any more detailed look as to what happens with different levels of slow stations and how bad the impact is on that? From the graph you showed, it didn't look all that bad in terms of throughput, but that is something that that may impact some people in a slightly negative way.
Yes. So for the first question, yes, we can now run WebRTC over Wi-Fi while other people are using the network and downloading, and I do this occasionally myself. I don't have numbers specifically for WebRTC in a testbed scenario, but from I run this code at home and it works. As for the other thing, I think if you go, I have some extra slides. So if you go the other way, bit more, this one. So this was a repeat of the experiment with 30 stations instead of 3 stations. And so this will sort of show you the worst case where the dashed line here at the very end is now the slow station going from about 400 milliseconds to almost 2 seconds of latency in the medium, 1.5 seconds. So obviously, we get a lot of improvement. So if you go back one slide, this shows you the difference in throughput when there's 30 stations. So we get sort of a huge improvement in aggregate throughput. But of course, if you have a very slow station, we are limiting it. And we do this by basically starving it until it slows down. And this means, this works, but if you are that slow station, you are going to notice, I guess. And of course, you go into sort of a philosophical argument. What notion of fairness do you really want to apply to your network? And so my reasoning is that since time spent transmitting on Wi-Fi is sort of the scarce resource, this is what we should be enforcing fairness on. Whereas the 802.11 MAC by default enforces throughput fairness, which is why this anomaly sort of appears in the first place.
Right. Well, that I certainly understand that point of view from a technical point of view. From a user level point of view, that may not be the sort of fairness that a user necessarily wants to apply, depending on the situation. There are some intermediate levels between throughput and airtime fairness, where you allow slow stations to have some level of additional airtime in order to keep them usable, okay, while not overly hurting the fast stations. And that might be something worth considering as an option.
So airtime fairness actually translates to proportional fairness at the throughput level, which is already a sort of trade-off between efficiency and fairness. Yeah.
And it didn't look like go ahead. I'm done.
Thank you, Randall. Can you ask your question offline, Andrew? I want to move on to the next talk.
I just had a little comment, but sure, I can do that.
Go on, make a quick comment before Neil. Come on up.
Andrew McGregor, just to say that the slow station problem is also rather mitigated if you have a multi-AP deployment, and that .11r will tend to move the slow stations to places where they aren't slow much more vigorously in the presence of airtime fairness. And so actually you get better throughput as seen from the station if there is an alternate AP it can talk to.
Thanks for that talk. That's actually quite a good piece of work. And we're going on to Neil and BBR. Take it away, Neil.
Thanks, Jenna. So my name is Neil Cardwell, and I'm going to give a quick update on the BBR congestion control project. This is joint work with my colleagues at Google, including Yu Chung and Stephen Sohail, the Quick BBR team, which is Ian and our illustrious co-chair, Jenna, and Victor, and then Van Jacobson as well. Next slide, please. So just a quick outline of what I wanted to cover. I wanted to start with a quick review of BBR and its background. If you want more details, there are some links to previous IETF presentations. The main meat of the presentation will be a quick overview of the new internet drafts we just posted about 2 weeks ago. The first is the delivery rate estimation algorithm that BBR uses, and then the second is the BBR congestion control algorithm itself. I'm going to speak briefly about active and upcoming work for BBR, because there are still things that we'd like to improve about it. And then I'm going to give a quick deployment update, which the news here being that we've switched quick traffic from Google and YouTube over to using BBR just recently. Next slide, please. So just a quick background. The motivation for the BBR project is really the sort of fundamental issues we see with loss-based congestion control, meaning Reno and Cubic largely. And basically the issue is that packet loss is not really a good proxy for congestion. These algorithms sort of assume that packet loss is equivalent to congestion, but of course that's not the case, and really bites us in a couple of important use cases. So for example, often in shallow buffered situations or cases where there are link layers that are lossy, you can get packet loss long before you can get congestion. And in such cases, loss-based congestion control gives you a multiplicative backoff every time there's a round trip time with a loss, and so you get pretty bad throughput. There are some examples here. So for example, to get 10 gigabits over a 100 millisecond round trip time, you need less than 1 packet loss per 30 million packets, which is tough to achieve operationally. And if we look at more realistic loss rates that we see over the internet or over high-speed WANs with commodity switches with shallow buffers, then you see more like a 1% loss rate. And there, with 100 millisecond round trip time, you're going to get around 3 megabits with the loss-based congestion control. At the other end of the spectrum, if you got really deep buffers, then we have the classic buffer bloat problem, because the loss-based congestion control will keep ramping up until it fills those buffers. Next slide, please. So BBR, so that stands for bottleneck bandwidth and round trip time, or round trip propagation time. And the core idea here is that we try to build an explicit model of the network path that tracks both an estimate of the bandwidth that's available to the flow using a windowed max filter, and then an estimate of the two-way round trip propagation time using a windowed min filter on the RTT. And we update that model on every ACK. And then we use that model to control the sending behavior. Largely what we do is a sort of sequential probing process, where first we probe for more bandwidth, and then we try to cut in-flight down to probe for the RTT and keep the round trip time low. And then we also do that while being aware of the model itself, in order to feed each aspect of the model the samples it needs on the timescales it needs. And then putting that all together, we try to seek high throughput with low delay. And in practice, what we see is that the algorithm can give you sort of the maximal available bit throughput up to about a 15% packet rate, which is sort of a parameter of the algorithm, not sort of a fundamental aspect of it. And then it also maintains a bounded queue that's sort of independent of the buffer depth. And if we want to put it in context, we can sort of quickly compare it to some more traditional congestion control algorithms that folks in this room are familiar with. So, in terms of the congestion signal that the algorithm uses, BBR, as we just said, uses a model of the bandwidth and the round trip propagation time, whereas Cubic and Reno use packet loss. Vegas uses RTT and packet loss. DC-TCP uses ECN and packet loss. And then if correspondingly we look at the primary controller that these algorithms use, BBR actually tries to use pacing rate as its primary control mechanism. It does also have the CWIND backstop, but it tries to do most of its action with pacing. Whereas the other previous congestion controls are built around a CWIN that sort of limits the volume of data in flight. Next slide, please. All right, so I want to dive into the first internet draft that we posted a couple weeks ago. This is the delivery rate estimation internet draft. And there's a link there, or you can Google it if the slides are not up yet. So basically the idea here is that on every ACK, this algorithm provides a sample that has two aspects. The first is an estimated rate at which the network delivered this most recent flight of data packets. And then the second aspect is it tells you whether or not that particular rate sample was application limited by the sender. That is, the sending app ran out of data to send at some point during that flight. And why did we separate this out into a separate draft? Well, I mean, we could have integrated it, but our thoughts were that first, this helps to break up the algorithm into smaller, easier to digest pieces. You know, we can think of BBR as having a sampling part and a modeling part and a control part, and this just helps it be easier to digest. Also, you can implement the bandwidth sampling separately, and in fact, in the Linux TCP code, it's definitely a separate algorithm. And then finally, it's also useful to think about bandwidth estimation outside of the context of congestion control, or outside of the context of BBR. The other congestion control algorithms might want this, or adaptive bitrate streaming might want this, for example, to pick which bitrate to show the user. Next slide, please. So the basic design principles that we were working from for this bandwidth estimator were, first, we wanted it to be purely passive, in the sense that we wanted it to work with the acknowledgements that we're already going to receive for the data that's in flight for that transport connection. Second, we wanted it to be generic and portable to different congestion control algorithms, different transport protocols. And so far, we have a Linux TCP implementation, a quick implementation, and then there's a FreeBSD TCP implementation underway at Netflix as well. And we wanted to also, as I said, track which samples were application limited. We wanted it to be relatively efficient, so constant time for each ACK that comes in. We wanted to try to err on the side of being conservative and underestimate. We wanted to make sure that we got feedback, whether we're in recovery and getting SACs, or we're not and we're getting cumulative ACKs. We wanted to make sure we can try to get an estimate at all times. And then we wanted to try to get an estimate that is over a time scale that is at least one round trip rather than one packet to try to filter out some noise. And if we think about alternatives, the main alternatives out there for bandwidth estimation that we considered were sort of packet dispersion metrics, looking at the interact spacing. And there are various approaches in that space, packet pair, packet trains, and chirping. But some of the challenges we saw with those kinds of approaches are that, you know, in the real world, with cable modems and Wi-Fi and cellular links, there are a lot of things, a lot of funky things happen with ACKs: compression, aggregation, decimation, stress jacks, jitter and noise in the queues. And so we've found we sort of took this particular approach to try to tackle some of those issues. Next. So if we dig down to the very essence of the delivery rate estimator, I think this is a good picture to keep in mind. The curve here that we're drawing has on the y-axis the amount of data that's been cumulatively delivered over, or acknowledged as delivered over the lifetime of the connection. And then on the x-axis, we've got time that's elapsed. And what we're really trying to show here is essentially the slope of the delivery curve. And a key part here is what is the time interval over which we are calculating that slope. And the key issue here is that we calculate the time interval, we calculate this the slope over a time interval that starts from the most recent ACK that we have received before we sent a packet until the ACK for that packet. And do we have a laser pointer here, or
we can try.
Anyway,
you can see if this works. Oh, there. I have one that does.
Cool. Can we go back to the previous slide? So the data, I didn't depict it very well, but the data packet in question here that's being sent is this one here, and that's ACK here, and then we go back to the ACK that was sent before that packet, and we use that as the start of this rate sample. And then we just basically calculate an ACK rate, that is the amount of data that was delivered between those two ACKs divided by the time elapsed between those two ACKs to give us that slope. And that's the ACK rate from this algorithm. Next slide. So you might ask, well, why can't we just use the RTT? And what happens is if you try to calculate an ACK rate, that's just the amount of data delivered divided by the RTT. You can see if we look at the same picture with that alternative attempt at calculating an ACK rate, that actually gives you an ACK rate that sort of badly overestimates the actual delivery rate, because it doesn't incorporate the amount of time that was really needed by the network to deliver all of those bytes that you are counting in your sample there. All right, next slide. So one big issue that you run into when trying to calculate delivery rates in the real world is what you might call ACK compression. There are similar effects going by other names that have similar issues: aggregation, decimation, stretch ACKs. Basically, by all of these, with all of these kinds of effects, we have ACKs that are delayed and then they arrive in a burst, or there's a single ACK that covers a lot of data that was delivered. And this can be caused by the receiver, can be caused by a middle box. But the big issue is that these are quite frequent in the real world. They're really common in Wi-Fi, cellular, cable modem links. And the issue is that you can, if you're not careful, you can run into excessive ACK rate samples. So I'll give an example here in the next slide. So here's a real world trace where the actual bandwidth was something like 8.9 megabits, but the ACK rate sample shown in red here is 27 megabits, and that's because of the ACK compression that you can see. There's a horizontal green section in the cumulative ACK stream that's a big silence, and it looks like then we get a burst of compressed ACKs all arriving at once, and that results in an overestimate in the ACK rate. So next slide. So the way that the algorithm currently deals with this is to sort of simply filter out the ACK rate samples that are implausibly high using the following observation. So basically, the ACK rate can't really physically exceed the send rate on a sustained basis for obvious reasons. And so what you can do is for each flight of data that's delivered between some send and some ACK, you can calculate the send rate for that flight, and then you can calculate the ACK rate for that flight. And then to help filter out these implausible samples, you can just use as the delivery rate sample the minimum of the send rate and the ACK rate. And this tends to do a good enough job in most cases. It can be improved. It's not perfect. It can be improved to filter out more thoroughly some of these implausible ACK rates, and that's an active area of work for the team. Next slide, Jana, if you get a sec. Thank you. So what this looks like on the picture is if we take that same example, here we would look at the ACK rate, which I previously showed you, and then the send rate, which is shown here in red. And in this case, we would use the min of the two, which is the send rate, and that gives us a safe, in this case, it's sort of an underestimate, but at least we haven't overestimated, and probably the congestion control algorithm, certainly if it's BBR, will be able to filter this out appropriately. All right, so I'm going to quickly zoom through some pictures. I won't go into the detailed notation here. This is mostly if you're reading the internet draft at some point and you want to know what picture can explain a particular equation that you're looking at, you can go back to these slides. So this is just a quick way to show what the send rate looks like. It's basically the slope of this green line. It's the amount of data that's acknowledged as delivered divided by the send elapsed time, the amount of time it took you to send that data. Next slide. Correspondingly, the ACK rate is just the amount of data acknowledged as delivered divided by the time it took to ACK all those packets. Next slide. And then the delivery rate is just the minimum of those two rates. Next slide. So the other thing I said that this estimator provides is a notion of whether a rate sample was application limited or not. And it does this with the algorithm that you could sort of read in detail in the draft, which I'll zoom by here. But basically, let me go up to the next slide. And this sort of shows you a picture. And basically, every time the application runs out of data to send, it marks the application as app limited. And then when all of those app limited samples are out of the pipeline, then we can exit that purple region where the samples are marked application limited, and then we can get back into this blue region where we've got non-application limited samples. Basically, in the interest of time, I'll skip over the details, but the idea is that when you're application limited, you get a sort of idle or silent bubble in the pipeline, and you just need to track when that bubble has been acknowledged and is no longer in the pipe and no longer pulling down your rate samples. Next slide. So let's move on to BBR. So the big picture here for BBR is that it takes as input these bandwidth or rate samples I was just talking about, along with good old-fashioned RTT samples that your transport protocol is probably already taking for retransmission timeouts. It takes those as inputs, and it uses those to build an explicit model of the bandwidth available to the flow and the round-trip propagation time. And then those two estimates get fed into a sort of probing state machine that increases and decreases in flight to try to keep a reasonable number of packets in the pipe, and also feed samples back into that model. And the output of that state machine, all that together, is a pacing rate. and a pacing quantum, a chunk size that you want to use for your pacing, and then a congestion window, a maximum amount of data you want to have in flight. And then that goes into the pacing engine, which chops up the data stream into those quanta, and then paces them out at the given rate and makes sure that the volume of data never exceeds that congestion window. Next slide. And so here's a quick outline of what we cover in the internet draft. It's basically a lot of the same stuff I just showed in the picture, so I'll try to breeze right through it. We cover the network path model, both bandwidth and round-trip propagation time. We cover the target operating point, which is that we want to try to maintain both a rate balance to try to match the available bottleneck bandwidth using our pacing rate. And then we also try to achieve a full pipe to try to keep the amount of in-flight data roughly equal to the estimated bandwidth delay product for our flow. And then we use the control parameters at our disposal, the pacing rate, the send quantum, and the CWIND to dial the knobs using the state machine to try to stay near that target operating point. Next slide. So here's a quick overview of the state machine. There are sort of four main states there. And the state machine sort of implements this two-phase sequential probing that in the first phase, we raise the amount of in-flight data in the network to probe to see if there's more bandwidth available and to get high throughput. And then once we've done that for a little while, then we go into the second phase where we cut the in-flight back down, both to probe for the round-trip propagation delay and to reduce the amount of data in the queues and get lower delays. And we do that on two different timescales. So there's the warm-up period when we've got a fresh new connection, and we've got this issue that bandwidth sort of spans 10 or 11 orders of magnitude from bits per second up to hundreds of gigabits. So we want to rapidly probe the network, and we do that in the startup state where we exponentially ramp up our sending rate, doubling it each round trip time as long as the delivery rate is also doubling. And then we look for a full pipe using a sort of looking for a plateau in the delivery rate. And then when we estimate that we filled the pipe, we enter the state called drain, where we cut the pacing rate to below the estimated bandwidth so that the in-flight amount of the in-flight data sort of gradually, or rather quickly really, drains out of the network until we've estimated that we've pulled our in-flight data down to the bandwidth delay product. And at that point, we sort of go into steady state where we do the same kind of probing, but on a more gentle amplitude. So the probe bandwidth state cycles the pacing rate up and down to do that probing for bandwidth and then draining the queue. And then if needed, then we can also do a sort of coordinated cut in-flight to probe for the round-trip propagation delay. And then the details for all of those mechanisms are in the draft. Next slide, please. So we're not done with BBR. We've got several things that we'd like to improve. Several known issues or known scenarios where we definitely want to get the behavior to be, we want to improve the behavior. So the biggest focus right now, or one of the big focuses right now, is on scenarios where there are high degrees of aggregation, and we want to improve both the bandwidth estimate. As we mentioned earlier, you can get bandwidth overestimates in these cases, and we're working on new techniques for filtering out these variations and getting a more reliable bandwidth estimate in these cases. And then second, we want to make sure that we're provisioning enough data in flight in these cases, because when you get these aggregation cases, often you've got a very long silence, sometimes tens of milliseconds. Even if your minimum round trip time is 1 millisecond, you might wait 10, 20, 40 milliseconds for an ACK. And so you have to make a sort of judicious estimation of how much data you want to have in flight given that behavior. And then another area of work is BBR's behavior in shallow buffers. There are some known issues where BBR can keep considerably more data in flight than we'd like if there are shallow buffers. It's still bounded to an estimated BDP, but if you don't have a BDP of Q to hold that, then the packet loss rate can be higher than we'd like to see. So that's a known issue where there's active work and discussion and testing on the BBR dev list. And then finally, there's also work underway to look at BBR's behavior in data center environments where there are large numbers of flows. Next slide. So in conclusion, there are 2 new BBR drafts out. We're happy to get people's feedback, suggestions, questions, whatever. We'd love to see feedback. BBR is now deployed for Quick, as I mentioned, on google.com and YouTube. That's the sort of latest deployment update. And the character of the results is similar to those results we saw for TCP, which we mentioned at the last IETF. So with that, now we have basically all Google and YouTube servers talking to the outside world, and then the Google data center WAN traffic on our backbones between our data centers. That WAN traffic is also using BBR. And then we see better performance than Cubic for web traffic, video traffic, and RPC traffic. The code is available as open source with links in the slides. And then work is underway, as I said, for FreeBSD as well. You can talk to the Netflix folks. And then we're actively working on improving the BBR algorithm, as I mentioned. And we're always happy to hear test results or look at packet traces. And next slide. And that's it. We basically have a landing page here on the mailing list. So if you search for BBR-dev, you'll get the mailing list, which has an intro message that has links to the internet drafts, the paper, the code, previous talks, that kind of thing. And we'd like to thank the folks below who helped us get to where we are today. And any questions?
Thank you, Neil. We have 5 minutes for questions. Randall, you're up.
Randall Justin Mozilla. Two quick questions. The small buffer issue that you're still looking at. Does that also include looking at things like AQM, various variations on AQM, and how well does that work? And what the second thing is, have you done any comparisons with the some of the proposed algorithms for ARMCAT, or how well it coexists with the ARMCAT algorithm, or planning to do that?
Yeah, so the work looking at shallow buffers would also, that effort also includes AQM. I guess so far we've done tests with Pi and Coddle. If other people have other algorithms out there they'd like to see testing with, let us know, or obviously you can do the test as well. So yeah, we are definitely looking at AQM as well as shallow buffers, since they have so much in common, obviously. And then we have not yet done tests with coexistence with RMCAT. That's definitely something that we like to do when we get time. Although if anyone out there has cycles to do that, that'd be great. Yeah.
Lars, this is a really hot mic. Not a technical question, but so I'll share the working group, and we are chartered to ship IETF Quick with an IETF standard congestion controller. The standard is, I think, quote unquote, but it should be in an RFC. But time and time again, BBR is being brought up as something, gosh, wouldn't it be nice if we could ship Quick with BBR? And we can't, because it's not currently sort of here. But I'm wondering what's your feeling on timelines, right? Do you think this might align? It's maybe also a question for Jana. Because it seems silly if we ship Quick with Reno and then do a rev 6 months later and do BBR, right?
Well, I'll defer to Jana since he's got a foot in both worlds, obviously. So,
Jana Iyengar, this is a deeper conversation, I think. Not because, so I think Reno for Quick makes sense at the moment because it's the simplest thing to document, yes, and it gives you completeness. But I do think that there's something to be said about actually, and I've talked about this in the past, about not actually having standards track congestion controllers at all, and having transports rely on sort of congestion controllers that are documented elsewhere. So
that is a larger discussion, which is I don't want to start it, right? But I think I remember that BBR was going to come in internet draft form, or maybe it's even here, and I guess it would either go ICCRG or TCPM.
Right, at the moment, so it is now published as an ICCRG.
So
yeah, it's published as ICCRG drafts as of like a few weeks ago. So yes.
So I guess now it's then.
It's a good time to have that conversation. Not here, but we should do this offline.
I've taken more than of those 5 minutes than I wanted.
Thanks for raising it, though. Okay, I'm closing the mic at this point.
Hi, Neil. Thanks for presenting this to us.
Yeah.
In the references that you had, you said there's a research paper. Do you mean the ACMQ paper?
Yeah.
Is it a peer-reviewed paper?
Yeah, research is probably the wrong word. Yeah, but I was referring to the communications, the ACM paper. Yeah.
Okay, and we used that one for our student reading group at Akamai, and people quite enjoyed talking about it.
Okay.
But I was struck by I didn't see a lot of evaluation or commentary from you as authors on prior work. Do you know, for instance, the one that I brought up to the students was the 2007 work by Kola and Mary Vernon called TCP Madison, that also is a model-based one. And I thought it was a nice comparison and contrast to yours, and I'd like to know what do you think is wrong with that? That caused you to do something different.
So I wasn't actually aware of that work. If you could email me a pointer, I'd love to read it. Yeah, thank you.
Yeah, I'll certainly do that one. And it was also a UDP-based implementation, my application. The one thing I can offer that you did definitely improve upon is there's required a change in the receiver. They could force an ACK, and that was the other aspect about where are you guys in deciding that you're just doing something that's based on empirical things about what the real internet today is doing versus what would you ideally like to change in the receiver that could make this maybe better?
Right. Yeah. No, that's a good question. Yeah. So we wanted to start with something that could work with the deployed receivers that are out there now, because we did want something that would work for both TCP and QUIC. But that's a very good point that there's probably a lot of leverage to be gained if you have a receiver population that you can iterate with quickly. So there are plans to look at what we can gain by receiver side bandwidth estimation for the quick transport implementation. So it'll be interesting to see what sort of gains we can get in that case. Yeah.
Rafael Secchi, University of Aberdeen. I was curious about what's been the development on when you don't have enough packet in flights to make up a reliable estimation. For example, if you have a sort of burst traffic like videos like Dash, where you transmit a burst and then you wait and then get another, and maybe between one and the other you don't have enough data to estimate the round trip or the throughput. What's the state of the algorithm at this point with this traffic?
Pardon, what is the treatment of that the algorithm has for application limited traffic? Is that what you're saying?
That quite very bursty, so that there is not enough data to make up an estimation like in the round trip where you probe at high speed.
Right. So the algorithm as it's currently structured does not do anything special in those cases. What it would end up doing is it would start out with the initial congestion window picked by the transport implementation, usually initial congestion window of 10 packets, and then it would from there it would calculate an initial pacing rate using the high, what we call the high gain, that can double the rate every round trip time, which is 2.89. So it would calculate 2.89 times the initial window per round trip time. So 2.89 times the initial window divided by the round trip time will give you the initial pacing rate. And then every time you get a bandwidth sample, it will look at that and decide if that's the maximum bandwidth that's seen recently. It will use that to update its bandwidth. And then it uses the sort of general approach of using that high gain times its bandwidth estimate to calculate the pacing rate. So it'll be 2.89 times whatever the biggest bandwidth sample it's seen. And while it's in startup, it's not going to reduce its pacing rate until it is pretty sure that it has filled the pipe using its regular pipe filling estimator. So those low application limited rate samples shouldn't cause it to decrease its sending rate. So it should be on the whole, for application limited traffic like that, it should be on the whole pretty similar to what you would get with Reno or Cubic in terms of the overall bit rate, I would think.
All right. With that, please catch Neil in the hallways or ask any of us questions about that. I have an insertion into the agenda. Roland has been doing some, well, thank you, Neil. Roland has been doing some experimentation with BBR as well. So just a few minutes on this experiment. Take it away.
Yeah, thanks for inserting me into the agenda ad hoc. So my name is Roland Bless, and I'm presenting some measurements that we did. Just only a brief heads up. This is joint work with Mario and Martina. Next slide. So we did some experimental evaluation in a small testbed using speeds of 1 gigabit and 10 gigabit per second, based on the Linux 4.9 version of BBR. And the testbed looks like this, where we have sender with basically 3 10 gigabit interfaces, software-based switch in the middle, and a receiver which is connected by a 1 gigabit Ethernet interface. The round trip time was 20 milliseconds, and we used a small buffer, which is corresponding to 0.8 BDP, more or less. So this is only a brief heads up presentation. So the full results will be in a research paper at the ICMP 17. And first we try to show that BBRs are working correctly in this setup. So single flow works as expected. So we get the whole throughput here of the bottleneck link. And also you can see the RTT is kept somewhere around the base RTT. So we have the probing phases here, the gain cycling, and then here, for example, the probe RTT. So yeah, that's working well. But the situation changes if we use multiple flows. Here in this case, we used 6 BBR flows, 2 per interface. And as you can see, this here is sender's transmission rate, actually, and the purple line here is the total amount or the aggregate. And that's way above 1 gigabit per second. So BBR is more or less in this case a little bit too aggressive. And since it just neglects packet loss as congestion signal, it doesn't back off here. So in comparison to that, next slide, please. Cubic works as expected here, so it doesn't send faster than useful. And here in this case, you can also see it by the numbers, like Cubic retransmissions for small buffers, also here for 10 gig per second, for example, in comparison to BBR, that's some orders of magnitude. So yeah, from our perspective, maybe neglecting packet loss as congestion signal is maybe not the way to go here. We have more results in the research paper, and we'll post a link once we have written up the final version, including the reviewers' comments.
Thank you, Roland. We can take a quick question. One quick question. Okay. Larry got it.
So this is Lawrence Bragman from Facebook. I've also done experiments with BBR, and I've seen that in some percentage of the cases, with even 2 or 3 flows, it gets into this state where one flow will get very high throughput, and the other flow will get like 110 to 100 the throughput. And other cases where one flow BBR, we think there's losses, but we would say it's not congested, and the other flows will completely back off from that. So I also have some concerns.
I'll let Neil respond.
Thanks. Yeah, I wanted to thank you all for this work. And I just also wanted to note that these all the issues that have been mentioned are well known and have been discussed on the BBR Dev mailing list. I would encourage people to subscribe to the mailing list and there are definitely this issue that you raise here is the one I was referring to earlier in my presentation about BBR's behavior in shallow buffers, and this is definitely an active area of research focus for our group. But thanks for the graphs.
Thank you so much. And we are now. Kon, can you come here for a second? I don't know which of these two presentations you're doing. Are you doing this one?
No. Yeah.
No.
Yeah.
This one?
Yeah.
Yeah. Okay. All right. And Kon is going to be, Kon and Bob are both going to talk about TCP Prague. Because we are in Prague, we have to do this. We have to make this a tradition. So every 2 years, I think we're going to have to talk about TCP Prague. But take it away, Kon.
It might be a disappointment because it is related to TCP Prague, but it's not about TCP Prague. It's about the foundations where TCP Prague wants to be built on. And well, anyway, let's start in it. So to give an overview of what are current evolutions and sometimes revolutions. So we see 3 streams of people working on congestion control. That's the people who have the senders under control. They think sender only and they try to optimize and get as much as possible done when only changing the sender. There are the network vendors who want to differentiate in their products and offer services for congestion control to work better. And then there is a third type where everybody has to collaborate together, and that's the hard part usually, where all the parties are impacted. And that's the L4S work and the TCP Prague, for instance. So in the sender only, there is a clear migration towards BBR, which is mostly delay-based, I could say, and there is also the concern about it ignoring drop. But of course, there is a network today which is usually not supporting a lot. There is no ECN, there is hardly any AQM. So it's the obvious thing to do. On the other hand, there are actions going on in the AQM working group, the second layer, where we have pi square, FQ coddle. Okay. Next slide. So also quite obvious, we all want to improve throughput and avoid buffer bloat. And in the third case, we also want to have really low latency and new class and to be compatible with Reno. That was the original strategy. So next slide. If we look more detailed, and we also did some experiments, this is how BBR works on tail drop. We did a test compared on a 100 megabit link on 20 milliseconds round trip time. So in BBR, it's quite good work and it works very well. It can achieve high throughput and full link utilization. So this is so we have here 4 flows, long running flows, and they evenly use the link capacity. And here we have about 100 requests per second. In this case, it's even 250 requests per second. And it's an exponential distribution of arrival time and a Pareto distribution of size, and this is the completion time. So, and the minimum based on the round trip time is quite low, and also the maximum is limited. So that's okay. And the queue size is also around 20 milliseconds minimum, because BBR is more like trying to measure what is the minimum packets in flight and enforces a little bit its amount of packets, and everything which is above that is stacked on top of that. So also the short flows that you see there, they're actually modulated on top of this minimum queue size that BBR sets. Okay, next slide. So if we compare that with Cubic, Cubic together with an AQM, that's then the second line of evolution, you could say. There we also have the target here is 15 milliseconds on a pi AQM, and there is, with a reasonable drop probability of 0.01% drop, we can keep the queue at 15 milliseconds, and the dynamic flows, they have also a good completion time. There are some limited loss, and you see that the dynamic flows are actually modulated around the 15 millisecond target. So that you could say it's a bit better or worse. It depends on your perspective, of course. Next slide. This is where we have data center TCP on a step AQM. So it's also how dual queue could work in L4S mode. There you see that the completion time is really low latency. The queue is with a step threshold of 1 millisecond very low. The other thing is that the variations for dynamic traffic are modulated below the queue size. So, and it's hitting a little bit on the utilization. So that's another compromise, but it guarantees you really low latency, no drop at all. So that's the other part. So all of them have their advantages and their possibilities. Next slide. But there are some concerns. And so initially there was, with Reno to Cubic, some compatibility with drop. But today, indeed, like was mentioned, there is no compatibility with drop. And there is, of course, then a kind of detachment between what's going on in this layer where we have AQMs and in this layer where we also want to be compatible with Reno. So in the next slide, here is an example. What happens if you put BBR on top of an AQM? So BBR sets the target to 20 milliseconds, and the AQM sets the target to 15 milliseconds. So it's the same as before. And of course, BBR sets its target, and the pi will increase the probability until finally, usually BBR detects the bottleneck as a pacer at the moment, and there are very high drop probabilities. And even so, you see here the drop probability is around 5 to 10% for several tens of seconds, and then only 1% for the other tens of seconds. So this is a problem. Next slide. So if we don't do anything, it will force actually operators to disable AQMs at the moment. And with it also a ECN, because ECN needs an AQM. So it's a bit of a problem and a concern, we think, and it should have a solution. And in the next slide, a possible solution could be, because it's actually not a problem. Well, actually both, we want to solve the same problem. BBR wants to have, as one of its main objectives, high throughputs under high round trip times and high loss conditions. But also L4S, we want to be compatible with the classic TCP, but we don't want to be compatible with their pathological cases. So we also want to have high throughput under these circumstances. So if both the systems could work on a corrected classic throughput behavior, which works with high throughputs under high loss and high round trip times, there is again a possibility for compatibility between L4S and the sender-only evolution, BBR. In the next slide. So as a possible solution, we were thinking on already for L4S, but it's equally applicable for BBR, to have round trip time independence above a certain round trip time, so that a flow of 100 milliseconds could be as aggressive as a flow of 5 milliseconds. Today, BBR is already having an opposite dependency on round trip time, so it's more aggressive the bigger the round trip time. So to be equally aggressive is at least a good compromise. On the other hand, we also want to be less responsive for high drops. So at a certain probability bottleneck or below a certain probability of the network, why not being scalable at that point? So for instance, if we make a classic congestion control responsive in a scalable way below 1%, we could always get around 24 drops per second, a very frequent signal. Also with the round trip time dependence, if you have 1% drop, you could also get 30 megabits per second, which is a high drop probability, 1%, and you get a reasonable high throughput as well. So next slide. Here, for instance, if we have round trip time independence above 5 milliseconds in this case, you will see this is throughput, so this is usually a rate, and there are two types of rates. There is the rate of the traffic itself, and there is the rate of the marks, so how many marks per second you get. So this set of lines are the rate, these sets of lines are the drops per second, you could say, and as you can see, what we propose is to limit it, so to always have 24 drops per second. If at 100 milliseconds and 1% drop probability in general, the Reno and the cubic, so we're having here Reno in cubic lines, the bottom lines here, they have around 1 drop per minute, which is not that much, and it's even going worse. You will see in the next slide. If we can make them all round trip time independent, they will always get 24 drops per second. Similar, with that amount of drop probability, there will always be at least 30 megabits per second of throughput that could be achieved. Of course, we can discuss about what should be the real thresholds or real values of these settings, but okay. In the next slides, there is also shown, so previously you saw here the round trip time. Here is the drop probability. So here is this high drop probability and a low rate, and here is a low drop probability with where we expect to have high rates. So if we see at Reno, this is the bottom line here, the throughput is limited. So with this amount of marks, it's quite low. With Reno, we could achieve only, well, 800 megabits per second on a 5 millisecond, oh sorry, on a 100 millisecond round trip time. Is that correct? Yeah, here we could go up to 200 gigabits per second. So on the 1% case here, you again have the 24 drops per second and the 30 megabit. So if you become scalable here, you can have much higher throughputs where, okay, the throughputs can be very high, but this amount of drop probability means that you only get 2 drops per hour or a half or 1 drop every 2 hours. So this is cubic. You see there is not much difference between cubic and Reno, but if we make it scalable, there will be always 24 drops per second. Okay. So we have a paper. It's not a published paper. Well, it's on the website describing all the different scalability requirements, and I've talked about those two. They were initially meant to be in the context of L4S, but of course they're also applicable in the classic TCPs. So if you want, you can read more in this paper. We can also have discussions about this. If you are interested in more of these experiments, there are a few videos that I've pushed to YouTube where you can see also experiments BBR running with an AQM and BBR running next to cubic as well. Okay. Thanks.
Thank you, Gon. Shall we take questions after Bob's, or?
If there are now questions related to this, otherwise.
Yeah, feel free to come up and ask questions. I'll transition to Bob in the meanwhile.
Hi there. Yeah, so we inserted that into the discussion because the tensions between these requirements still applied for all congestion controls, which is why we thought, well, we were trying to do a lot of work to work out how to make BBR meet these requirements, particularly, you know, as Kun has said, in this case where you've got someone trying to help with putting an AQM in and someone trying to use BBR, where we have this toggling behavior. So I'm now going to talk about tension, how these tensions might be resolved in the space where you've got a bit more freedom, because we've created this other queue for L4S, and so we can put a better end system congestion control and a better AQM in, so that they work together, rather than we haven't got any legacy to deal with in that queue, except to do with its coupling with the old classic queue. And that's why we started to try and sort out BBR's problems, because that we were coupling to that, and because it was ignoring the losses, it was starving us in the other queue, even though we'd tried to get away from it, sort of when we had an AQM, and it was also starving all the other cubic flows and things like that. So this is now the context of my talk, as opposed to Kun's, is more about, okay, so what tensions have we got in this cleaner space? I call it a clean slate, an incrementally deployable clean slate, right? Because it gives you both. And what I want to try and do is explain some of the problems that we're trying to solve in the small amount of time we've got, and also because we sort of shifted our focus a bit to BBR over the last few months, we've not actually got any code. We've got a lot of code that tries to solve all these problems, and we feel we're still on the right direction, but I wanted to try and just explain the problems, and because they're actually problems that haven't really been articulated here before. So the first one, if you look at the utilization of 3G versus 4G versus 5G, there's a nice study at reference 1 that finds that 4G utilization has gone down and the variance of it has gone up. And we also did some simulations on a millimeter wave wide area 5G radio network, where we found that you can get a really high capacity, and what we measured that capacity by just flooding it with UDP with no congestion control on it, to see how much came out the other side compared to how much TCP was giving you as your good put. And so the message here is that the more radio capacity you get, the less your utilization is by quite a large margin. It's going down to 22% here, and you can see the whisker there represents the 1 standard deviation of variance in that capacity, and that's why there's a problem. And I'll show this when we look into it, what's going on. So the whisker in the amount of capacity is all the variation in the capacity, and TCP just can't move fast enough to take advantage of that variation. One other point to note, the last bullet on here, the utilization was actually a lot worse, but we manually fixed another problem so that we could just look at the congestion control problem, so that utilization for 4G was actually only 43%, but that was because of a combination of the problem here that of the variation of the capacity versus the congestion control, and a problem with the receive window tuning, where the auto tuning couldn't cope with the dynamics either. So you're actually getting only 43% utilization of a 4G network, and that was measured using a real network, looking at all the traffic in that network over a period of time. So together we calculated that if, for instance, we could increase that utilization to say 85%, not not a really ambitious target. I did a back of the envelope calculation. 1.1 trillion euros was spent on spectrum licenses in the European Union. And if you increase the utilization of that from 43% to 85%, you have actually released 460 billion euros of investment in Europe. And that's just Europe, because I only had the figures for Europe. Right? So sort of utilization is worth fixing when bandwidth costs that much. Right, next. So this is why, half the reason why there's such poor utilization. As I said, the other half is just receive window tuning, which you would think we could sort out fairly quickly. So this is the radio capacity, and the orange is cubic TCP underneath it. And it's essentially bouncing along under the minima because it's taking far too long to respond. You'll see this is in the 5G case. This is a screenshot of this simulator, which is simulating pedestrian mobility using 3 aerials, each of different frequencies. So there's a low bandwidth flood, a wide area flood, and then there's higher bandwidth at higher frequencies that are much more directional, so you only get them sometimes. And so that's what's giving you these peaks, but essentially it's really only using the low bandwidth flood. And this is why, in this case, for the simulation, the utilization was 19%, because you can just see the cubic curve just starting to curl up there. You see, there's each of these grid squares is 10 seconds, and so that's over about 20 seconds. It just starts to curve up, even though the round trip time here is 20 milliseconds. So it's 100 round trip times. It's just starting to get moving, right? And next. So I had a look at Wi-Fi as well. 802.11ad is also the highest bandwidth Wi-Fi. You're just starting to be able to buy these. 3 gig channel. In measurements in a static office environment, I should explain that 802.11ad doesn't go through walls. So it's intended that you have an access point in every room. And also you're not allowed to move around. No, not true. But other people aren't allowed to move around. Mobility is okay, but shadowing is not, so they mustn't get in the beam. However, it does have it can pick up reflections and things and get round shadows, right? So with testing compound TCP over this, we got a median good put of, even in a static situation, but with some humans moving around in an office, you got 280 meg out of a 3 gig channel, 3 gigabit per second channel. So again, very low utilization. With the beamforming, we didn't do this ourselves, but using the beamforming goes up to 16%, but it's still not really using all this hard work that the layer 2 people have done. And so, this is a message for people here. This stuff is a challenge for congestion control people to start working on the dynamics. Next. So we learned these lessons about 10 years ago when everyone was doing high-speed, high bandwidth delay product congestion controls. And we learned you should not have too many round trip times between each loss. That's the problem with Reno. As it gets faster, the sawteeth gets so big, the recovery time. And so you can see here why we're getting a problem, in that Cubic was the result of that research, but Cubic's now becoming unscalable. If you, Cubic here at 100 meg, if you multiply its rate by 8 times to 800 meg, the distance between, or the recovery time, goes up from 250 round trip times to 100 round trip times. No, sorry, 50 round trip times. It doubles, yeah, to 50 round trip times from 250. So I'm using this variable v to mean the number of signals you get per round trip time. And so the trouble is it's getting smaller. Whereas data center TCP, you can just see these little saw teeth here. You're actually getting 2 signals per round trip for data center TCP. And so, and it stays at 2 whatever the rate. That's the point of why we call it scalable. And it means you're getting a lot more information all the time rather than just sort of having to launch off into space until 500 round trip times later you get another signal and you don't actually know what's happening. So next. I'm not going to go through this. This is just to record some very simple maths that essentially says that you need to make sure in your TCP equation that the P, the loss level or the ECN marking level, the power of it is greater than 1. So with Reno it's a half, the cubic is 3/4. As long as it's 1 or greater, you're okay. And that's what we mean by scalable congestion signaling. That means your saw teeth don't get larger as you go faster. And that also means they don't cause more delay variation. All right, next. And so the point about this and how this links with the radio stuff I just mentioned is that when you get a capacity decrease, you immediately get some signals and you can drop away very quickly. It may take 1 or 2 round trip times if you've got to drop down by 10 times the capacity or something, or 1/10 of the capacity. But when there's an increase, you just get nothing. You get no information. And so if you have a very frequent signal that's, as in the DC-TCP case, every 2 round trip times you're getting a signal, when that goes away, you know within 1 round trip time it's gone away because you're not getting any these 2 signals every round trip time. Whereas if you only get a signal every 500 round trip times, it takes you at least 1,000 round trip times to think, hang on, I haven't had a signal for quite a time now, and I was expecting one after 500. Right? And so if you're getting a signal very frequently, you also know when it's stopped. That's the main point, and then you can start probing. And
Bob,
yep.
You have a few minutes left.
Okay, yeah, I think I'm nearly done. I've got a couple of slides. Next, yeah, we can go to next. Oh no, there was one very important point on that. Yeah, and so with the ACK rate measurement, that is a way to find out that the capacity has just increased. But for us, it becomes very difficult when we're trying to get the queue to nearly nothing to ever see that, because you've only got a few packets in the queue, and so you miss that and you need something else. So if we are, for the problem we're trying to solve, which is very low latency for the new applications like VR and all the rest of it, we can't really use ACK rate pacing, ACK rate measurement. We've been trying, but it's hard. So that was really an explanation of why we have this first requirement that in the paper about scalable congestion signaling, so that we get enough signaling. The second requirement is limited round trip time dependence, and here is a very, very brief example of that and why it's never been a problem in the past, because we know we've had a problem with round trip time dependence for years, and we've just lived with it and it's been fine. The problem is that as your queue gets smaller, it takes out a cushion that was protecting you from this. So say, for instance, you've got 200 millisecond round trip time versus the 2 millisecond round trip time flow. So there's a 100 times difference. If you've got a queue of 200 millisecond in a drop tail queue, your actual round trip time is 400, and the other one's actual round trip time is 202. So you've actually only got a difference of 2, and that's why we haven't worried about the problem. It never gets greater than 2, right? Because you've got this, generally, drop tail queues are built to be about the worst, the rule of thumb of 1 bandwidth delay product. So, but when your queue gets down to here, where we are at the moment with Pi and such like, you're starting to see round trip time dependence getting a bit worse. And the queues we want and we've got in L4S, you're then getting close to the 100 times difference. And so round trip time dependence becomes much more important because the larger round trip time flows start to starve, right? And I'm not saying this is an anti-starvation, so that not shouldn't be there. This is an anti-starvation requirement, not a strong fairness requirement, right?
Bob, we have 1 minute.
Yep, next. So how do you solve that problem? The tension between this scalable signaling requirement for the capacity variation stuff and all the dynamics and this article dependence. And if you rearrange the maths to make this clear, in one case, P times the window has got to be greater than a floor. In the other case, it's got to be proportional to round trip time. They're clearly incompatible. Next slide. So the way to solve this, or the only way we can think to solve this, sorry, not the only way, we've thought of some other ways as well, but this is the favorite at the moment. Once you know your round trip time at the start of a flow, you work out this, and then you use that as your constant for your additive increase, instead of just 2, as in the case of DC-TCP, you get this value that depends on the round trip times you measure. And then you get a floor, or a very slowly decreasing congestion signaling at low round trip times. So you've got effectively a floor to your signaling. So you're getting still, even at 10 nanoseconds, you're still getting 1 signal every 10 round trip times. But you're getting your round trip time independence at high round trip times, and it's not actually completely round trip time dependent at low round trip times. So with that formula, and it's implementable because you only do this calculation once, or maybe twice if your round trip time changes significantly. So in all, we believe we've got a compromise between those first two rather difficult requirements to reconcile. Last time we talked about unsaturated signaling. We had a solution to that. The dual queue obviously gives you the coexistence, and we're trying to work on fixing BBR enough so that we can still coexist with it. And then here's links to the paper, here's links to the videos that Kuhn showed. And if this were the PDF,
we don't have time for questions.
Right.
Thanks, Bob.
Yep.
And please grab Bob in the hallways and ask him questions. We're going to move on because we have 28 minutes and 3 more presentations to do.
Good.
The next 3 presentations are going to be 10 minutes each, so please try to stick to that. Is that okay? Right. Anais is going to go up next. I'm going to try and pull up the presentation.
Good afternoon. I will talk about improving core network scheduling with the burst limiting shaper. First, before diving into our proposed solution, I will do a quick recall of the current architecture. Next slide. So the core router architecture defines 3 classes: the expedited forwarding class, the assured forwarding class, and the default class. So the expedited forwarding class is for real-time traffic, for example, voice over IP, and it's scheduled with the first priority of the priority scheduler. The other 2 classes, AF and DIR, are scheduled as the second priority of the priority scheduler using a rate scheduler. The key features of the rate scheduler is the fact that it limits the capacity available to the AF to prevent the starvation of best effort traffic due to the elastic nature of the AF class. Next slide, please. So let's take an example here. On the x-axis is the weight, the relative weight of the AF class, and on the y-axis is the AF output rate. And so if we take an example, for example, with an EF input rate of 50%, we can see here in red the desired behavior when you vary the weight of the AF class. So next slide. If you want an AF output rate of 25%, you will of course set a weight of 0.5 to get 25 as the AF output rate. But if we don't know the EF input rate, or if it varies, for example, from 25 to 75%, you don't get 25% for the EF output rate. You get a output rate ranging from 12.5 to 37.5. And so the range you get is 25% of the capacity, and you don't know exactly what is the output rate you would get. And so we can say that when the EF input rate is unknown, the AF output rate is uncertain. And our goal here is to make the AF output rate more predictable. We want to make it more predictable, but we don't want to impact the real-time traffic, the EF class. And so what we seek to obtain here is the desired behavior, here in red. It is the same as before with the red scheduler, but we want the minimum between this desired rate and the EF, the residual capacity left by the EF input rate. So here, for example, it's 25% with the EF input rate of 75%. So when we consider all the relative weight for the AF class, you can see here in gray the uncertainty area you find yourself in when you consider the AF output rate. And with our proposition, you get reduction of the uncertainty areas. So now that I've presented our goal, I will explain more in detail our proposition. So it's based on the burst limiting shaper. It's a credit-based shaper which is proposed by the time-sensitive networking group, and its key idea is to use a credit counter to change the priority of the queue. And so here you use the transmitted traffic to update the credit. When the shaped traffic is sent, the credit is increased with a rate I send, and when the credit and no on the other case, so for example, if no frame is transmitted, or if the frame is from another queue, then the credit is decreased with a rate of I idle. Then for the credit change, it's happened in two cases. If the credit is high on the credit, and if the priority of the queue is high and the credit reaches the max level, then the priority of the queue becomes a low priority. Or if the priority of the queue is low and the credit reach a resume level. And so you can see that when the priority of a queue is changed, it will reserve a certain amount of bandwidth for a shaped queue. Thank you. And so we worked on the burst limiting shaper, and we did a formal analysis using network calculus with Adam Mifdaoui and Fabrice Française. We also did a complexity analysis, an NS2 prototype, and a multiple simulation, and those results are currently under submission. From this work, we found out that the BLS has a low complexity, it is hardware implementable, and it has a key feature. It can limit the capacity available to the shape queue. And so when we consider the BLS and the priority scheduler, they behave much like a rate scheduler. And so this is why we decided to try and change the rate scheduler in the RFC to set a burst limiting shaper instead. Thank you. And so here is our proposition. We set the burst limiting shaper in the AF class. So the EF class is not impacted by the change. It's still the first priority of the priority scheduler. The EF class the EF class priority changes from 2 to 4, depending on the credits, as I explained previously. And so sometimes the default class for best effort traffic has a priority higher than the elastic traffic, and sometimes it has a priority lower than the elastic traffic, and this is how the burst limiting shaper can limit the capacity allowed to the AF class. Thank you. Next. Okay, so we did several simulations using NS2. First with a weighted round robin to for the red scheduler. Here on the left are the results. As expected, we have the desired behavior here in red, and it is framed with the behavior when we consider an EF input rate of 26 or 76%. On the right, you have the result using our proposal with the BLS, and you can see that when considering EF input rate of 26 or 49%, we have the desired behavior. With input rate of 76%, however, we have the desired behavior up to a weight of 0.5, and after that, we have the output rate, which is equal to the remaining capacity left by the EF input rate. And so I think you will recognize the previous figures with the uncertainty area, which is much reduced with the burst limiting shaper compared with the weighted round robin. And so we can conclude that the EF class is not impacted by the change. The BLS parameter can easily be calculated from a current configuration when you consider an expected EF input rate. When the EF input rate is known, the BLS and the weighted round robin have the same AF output rate, but when the EF input rate varies, the range of possible AF output rate is much reduced with the burst limiting shaper compared with the weighted round robin. And as a perspective, we hope to propose a draft in the AQM working group. And thank you for your attention.
Thank you so much, Anais. There's time for a quick question if there is one. Where is next? All right. One quick suggestion: you may want to actually talk to the TSVWG working group chairs instead of the AQM ones, and they're sitting right there. Take it away.
Okay, so I'm going to quickly talk about NEAT and how to use it to optimize a mobile communication system, kind of. So next. The outline, first some words about the ossified internet, then NEAT and how it maybe could be used to solve this, and then NEAT for mobile communication. Next. Okay, the internet today is kind of ossified. And the reason for this is that we have used protocols and combinations of protocols that has worked kind of good. So everyone has used it for some things. And when everyone has used it, the kind of infrastructure has adapted to it. This is, of course, not good because new things like new protocols and so on and such are not supported by this adopted infrastructure, and this leaves little room for improvement. Next. So one solution to this could be NEAT, which enables the use of transport services instead of transport protocols. It's an implementation of TAPS, and it can provide services like reliable transfer, multipath communication, low latency services. NEAT tries to map application requirements to services. So an application could say, give me a low latency transport service. And transparently to the application, the NEAT system will give you that kind of transport service. So NEAT tries to overcome the problem of ossification by providing a more expressive API that allows applications to say stuff like this, like give me a low latency service, so that the application doesn't have to bind to a certain protocol at design time. The other point, which we will see later, is using local and remote information to make well-informed decisions. And thirdly, NEAT uses happy eyeballs to kind of test the services it creates. Next. So, quick example. We have an application that wants to have a low latency service.
it asks the NEAT API for that in JSON. This requirement from the application will end up in the policy manager. The policy manager will try to match this low latency requirement to policies that are stored in the PIB there, the policy information base, and also match it with characteristics found in the SIB, the characteristics information base. So in this PIB, there will be a number of different policies, policies for high throughput communication, for multipath, for whatever. But in this case, we want a low latency. So the policy manager tries to map this low latency property to different policies and to different characteristics and build a list with different transport solutions. It could be TCP with this and this and this socket options set over this interface, because interface information and information like that are available in this characteristics information base. And then the policy manager will try to resolve this requirement into a list, and this list will then be handed off to the happy eyeball mechanism that will try to open the services. So next, and in this particular example, we get a match because we have a low latency profile that says that we are going to use TCP as a transport, and awkwardly enough, TCP no delay set to false for low latency. So it's kind of a typo, but yeah. Okay, so we kind of thought a bit about what to do with NEAT, and we had a bunch of mobile nodes in the department with mobile broadband support and also Wi-Fi support. So we thought, hey, why not test to use NEAT and MPTCP together? Because currently MPTCP is not optimized to this use case. It's more of a general transport protocol, right? So there are some details in MPTCP that aren't perfectly aligned with a mobile node communication kind of use case. So let's see if we can do something about that using NEAT. So we kind of have this set up. We have three kind of main problems if trying to communicate from this client to the server. So depending on the size of the object that you want to transfer, for instance, it can be costly to set up a multipath connection. So in some instances, it might be better just to have a single path because it's basically not worth it. The second thing is if we have link technologies that are very asymmetric in terms of performance. Let's say that we have very, very, very good Wi-Fi and maybe 2G or 3G connection. Then it might not be a good idea to include the bad one at all and just run single path because it can hamper the performance of the entire connection. And then we have a third one that we absolutely don't have time with, so I will skip that. Next, this was the setup we had. We had a regular server running Linux with multipath TCP and Monroe node. Monroe is a European project that builds a large mobile broadband test bed, and these clients are kind of good, small clients having both Wi-Fi and mobile broadband support. And the good thing with them is that it continuously measures metadata about what kind of access technologies are we currently having on the mobile broadband interface, signal strengths, and so on. And this can be just plugged into NEAT so that NEAT knows, so NEAT has that information. Next, the experiment was very simple that we did. We had a client, the client downloaded a set of files from the server using TCP and MPTCP with the regular socket API, and then we used NEAT. So the first thing, is it costly to set up? Well, if you look at the graph, you have the size of the different files on the x-axis and the relative download time on the y-axis, and it's relative to TCP. So for short flows, you don't gain anything by using MPTCP. You actually lose some. But for longer flows, longer than 100 kilobytes in this particular setup, you gain a lot.
NEAT, on the other hand, was able to track this at all times. So it effectively built the transport service using TCP for the smaller flows and then TCP on the larger ones. And how is this done? Well, this is a kind of simplified view of it, but the policy manager and the policy that we made for this particular experiment was simply stating that if we have a small file, in this case less than or equal to 100 kilobytes, or we had the link technology on the mobile broadband interface that was poorer than 4G, then choose TCP as a basis for the transport service. Otherwise, choose MPTCP. So, next. On the left, you can see the same experiment as previously, and that was when we had the Wi-Fi and the 4G connection. So when we change the 4G to 3G, we can see that we are starting to lose a lot by using MPTCP, regardless of the size of the flow here. And it has to do with several things related to MPTCP. And as you can see, NEAT does not choose to use MPTCP at all in this case. And that was, of course, because we specified that policy not to use it if we had a link technology worse than 4G. But this is just examples of how you could make the policies. And I guess we don't have time to choose to view the last one, so we jump there. So NEAT is an implementation of TAPS. It can compose transport services based on application requirements. And yeah, questions or no?
We do have time for one question if anybody has one. Thank you for keeping it tight. All right, thank you, Per.
We did have, Jake Holland. On Jabber, we had one question from John Leslie. How can we design this to minimize setup time?
I think this question is for Per.
Sorry?
It's for you,
yeah.
I think. Do you want to answer the question?
So again, sorry, I didn't.
The question was how do you use this to minimize setup time?
Yeah.
I mean, you can. It solely depends on the policy that you use. So you can choose to use a protocol that has less kind of setup time, or choose to configure a protocol with an option that gives it less connection time. But that would be about what you can do.
All right, thank you. Well, take it away, Michael.
So, hello, my name is Michael Met. I'm from the University of Tübingen, and I present joint work with Nicolas Zeitler. So this work is about activity-based congestion management for fair bandwidth sharing in trusted packet networks. This work is inspired by congestion policing using congestion exposure. That is work that was carried out some years ago in the IETF. So this is not an evaluation of congestion policing using congestion exposure. It's rather work that is inspired by its philosophy. So the problem is we have a bottleneck link that is shared by multiple users where congestion may occur. Flows may use different transport protocols like UDP are not reactive, or TCP which are reactive, and that can lead to unfairness. Some users may transmit multiple flows, others only a single one. So how can we share bandwidth fairly among users? One solution is if packets can be related to users, we can use weighted fair queuing. That enforces per user fairness for bandwidth sharing. if packets cannot be related to the users, weighted fair queuing cannot be applied, and here ABC comes into play. So this is the basic architecture of the ABC principle. It is a per domain concept. We have access nodes and we have core nodes. The access nodes, the user equipment is connected to these access nodes, and the access nodes meter the user traffic and add an activity value to the packets. This activity value is monitored by the core and access nodes, and they run an ABC AQM to drop packets during congestion. And for packets that have a high activity value, they get dropped with a higher probability than packets with a low activity value. And that leads to fairness between heavy users and light users. So that is the basic principle. What is activity? Well, every user is assigned a reference rate. That is a fairly low rate, which is way below the fair share of every user in the network. And we kind of measure the recent transmission rate of a user, and the fraction of this transmission rate and the fair rate of and the reference rate of the user gives you more or less the activity. So the activity is a multiple of the assigned reference rate of a user. And the higher the activity is, the more a user has sent in the recent past. Well, this activity can be metered by a scalable algorithm. I don't go into details here. What about the core nodes? The core nodes observe the packet stream, they monitor the activity of the packets and take an average of them. So they basically do a weighted moving average of all the activities observed in the packets. Then we use some existing AQM-based AQM mechanism that is based on drop probabilities. And the idea is now that we distort the drop probabilities in such a way that we get smaller drop probabilities for packets with a low activity and higher drop probabilities for packets with a high activity. And in sum, that leads to more fairness. In our evaluation, we used a very simple AQM. I don't go into details here. And this is the experiment setup. We have two groups of users. We have one heavy user group, which sends 10 TCP flows, and we have another light user group, which sends only a single TCP flow. And the traffic enters the network over an access node which does this activity metering. So here the activity information is added to the packets. And then we have a core node that is connected to the bottleneck link. This core node senses all the activities, does the averaging, and applies the distorted packet drop probabilities. Here are the results. The performance metric is the throughput ratio. What is the throughput ratio? The throughput ratio is the average throughput of the heavy users divided by the average throughput of light users. And if you have a throughput ratio of 1, that means perfect fairness, because the heavy users have the same throughput as light users, as any light user. Here are numerical results. So the first row shows you the delay of the bottleneck link. The second row shows you the user configuration. That gives you the number of heavy users and the number of light users. So it's one heavy user and 10 light users, for example. And then we have a third row that is the differentiation factor. This differentiation factor is a configuration parameter for the ABC. A differentiation factor of 0 means ABC is disabled. And for that case, we get a throughput ratio of 10. Why? Well, it's clear because heavy users have 10 TCP connections, while light users have only a single TCP connection. Then heavy users, without doing anything in the network, have a 10-fold throughput. So what happens with ABC? With ABC, we get a throughput ratio of around 1, and that requires a differentiation factor of 3. So that works quite well. So what else have we done? We have considered the reference rate, which is a configuration parameter for the system. We understood that it needs to be set to a rather small value, which is way beyond, which is clearly smaller than the fair share of the users. What else have we looked at? We have looked at the coexistence between non-responsive users, say a heavy user that sends UDP traffic without congestion control, and light users with only a single TCP flow. On the x-axis, you see the transmission rate of UDP users. And as the transmission rate of this unfair UDP user goes up, the throughput ratio also increases if we do not use ABC. That means the UDP user can starve all the other users in the network. And when we enable ABC on the network, we can see that we still get pretty good fairness, although the UDP user wants to send 5, 10, 15, even 20 megabits on a 10 megabit link, but the UDP user cannot hurt the TCP users anymore with ABC. Another experiment showed that we can reduce the upload time for a light user with another parameter, which is the burst tolerance. So ABC has a burst tolerance that can be used to tune the system so that we can increase small uploads. This work is related to the core stateless fair queuing work from Ian Stoiker, which was carried out 14 years ago. The difference is that with this core stateless fair queuing, we required rate measurements on the nodes, while in this work, we leverage active queue management. And this gives some nice perspectives. In particular, this work is extensible towards low delay communication, so it's possible to enforce both fairness and low delay. What are the use cases? The use cases are basically those that we had already for congestion exposure. It's fair rate sharing and improved quality of experience for light users. There were some drafts that congestion exposure may be applied in data centers. There's also an RFC that connects may be applied for mobile access networks. And there is another perspective, namely ABC may protect light users against heavy UDP users. In other words, it may be used as a defense against denial of service attacks. So, conclusion and outlook. Activity-based congestion management uses access nodes to add activity information into packet headers. Access and core nodes use that information for preferential dropping in case of congestion, and that enforces per user fairness, so that heavy and light users can coexist in a fair manner. The overall concept is protocol independent, and it leaves the core network stateless. I presented some simulation results that show that the differentiation is quite effective. We understood the configuration parameters, for example, this reference rate, which is most important, and protection against non-responsive traffic is possible with ABC. It's also possible to reduce upload times significantly, which can be also tuned by a parameter. ABC supports different user profiles, so it's not necessary to set the same reference rate for all the users. So different user rates are possible, and envisaged use cases are the same as for congestion exposure. Further work can combine ABC with Pi, for instance, to achieve both fairness and low latency. And we also would like to adapt ABC towards different service classes. This work has been published at the NOMS conference last year, and a preprint of this work can be downloaded from my website. That's about it. Thanks. Any questions?
Bob, very quick.
Your activity factor, it's about relative rates?
Yeah, it's about relative rates, yeah.
So does that mean it's instantaneous?
It's what?
Instantaneous?
Yeah, it's pretty much instantaneous, yeah.
Okay, so there's no history. So a light user that's sort of doing a lot of short flows versus a heavy user that's doing one or multiple big flows, the light user doesn't get any benefit from not being active at all, if you know what I mean.
You can have a history on it, because you have options how you do the metering at the access node, and if you want to have more history there, you need to apply a larger memory on the rate metering, and then you can have this memory.
Okay, but that's sort of arbitrary, what that time should be and all the rest of it.
Mm-hmm.
All right, thank you very much, Michael, and thank you everybody for trying to stick to your times. We have run over time by 6 minutes, so please ask Bob for cookies if you want any. I'm picking on Bob. Thank you everybody, and we'll see you next time. I did a good thing with putting it. I mean, I think I'd like to have more on each presentation, and unfortunately, this just makes it so that you're like cracking the thing, which is not fun. So, thanks again. Good to see you. Oh, for folks who are looking for the slides, I've uploaded them, so you should be able to find them online now. They're all uploaded, yes. They may take a few minutes to show up, but yeah, they should be there. Okay. If you've got the blue sheets, please bring them up here.